Okay, we are at chapter 10, rotation of a rigid object about a fixed axis. So let's get on with the lecture here. Here they're just talking about, we're going to discuss torque. Um, uh, those of you that remind me to show you the torque demonstration in the lab. I think it's a good demonstration of what torque means. But let's go on. Okay, we're going to talk about angular position. So we're going to talk about angular position, angular velocity, and angular acceleration. And they have counterparts in the linear world, position, velocity, and acceleration in a straight line. Now we're going to talk about it in circular motion. So we start with angular position, and to define an angular position for the disk, this is a cartoon image of a CD compact disc. A reference line is fixed in space. A reference line fixed in space is chosen. Typically, when you look at rotational graphs, the 0 point is typically at the x-axis, at the positive x-axis. That's where we start, and we rotate counterclockwise. Counterclockwise is positive x. If you were to go clockwise, that would be negative x, or I said positive theta. If you go clockwise, that's negative theta. So a particle at P is located at a distance r from the rotation axis through the origin. As the disk rotates, the particle at P moves through an arc length S on a circular path of radius r. The angular position of P is theta. That's the angular position is theta. Theta is equal to the distance S traversed by the point divided by the radius. So the circumference is equal to 2 pi r, 2 pi times the radius, which is equal to 360 degrees. And that corresponds to 2 pi radians for every circle. Now I'm gonna switch to an image that probably a lot of you know, and that's good. But some people don't think about it. It's the whole image of pi. If we draw a radius here, if we take that length, that's what this line is here. This is one radius. This is one radius marked along this circle, and that happens to be 1 radian. In other words, it's one radius marked along a circle. Well, how many of these fit in a circle? Well, we have, oops, sorry about that. Wrong. There. Let's get rid of that. We have 1, 2, 3, 4, 5, 6, and a little bit more, 0.28 something. Now let's look at it just in the half circle. How many of these are there? Well, there's the 1, 2, 3, and a little bit more, and that little bit more is the 0.14159, and it goes on and on and on. So pi is simply a ratio of the diameter. In other words, this being the diameter, let's change color here. This is the diameter. So this diameter fits across 1, 2, 3, and 0.114 times across the around the circle. But when we're talking about radius, the radian, it fits around 6.28 times. They're about 6.28 times around the circle. So just something I want you to be aware of. A lot of people, well, pi is just pi, but there is a physical interpretation of what that means. So let's go back to the PowerPoint. Okay, so there's 360 degrees, 2 pi radians in every circle. Once around the circle, there's 2 pi radians. 1 radian is equal to about 360 degrees divided by 2 pi, which is about 7.3 degrees. To convert from degrees to radians, if you have degrees, you multiply by pi and divide by 180. Basically, you're taking a ratio of the degrees, theta degrees. Let's say you have 90 degrees divided by 180. Well, that's 1/2 times pi. It's pi over 2. Now, if you're given radians, if you're given it in radians, you divide by pi and multiply by 180. It's a very simple conversion. Okay, so getting back to the angular position, theta is equal to S divided by R, S divided by the radius, and S equals the radius times theta. Now, notice that if you were to move that same theta, angular position theta, at a point further out, the S would be larger. By how much more? By the larger radius. So S is equal to R theta. Okay, so to define angular position for the disk, a reference line fixed in space is chosen. A particle at P is located at the distance R from the rotation axis to the origin. So here is angular speed. We can look at, there's a theta final and a theta initial. Now, remember when we were talking about linear speed, we were talking about the delta x over delta t. Well, here it's going to be delta theta. Since theta is angular position, angular speed is delta theta divided by delta t. So the omega, the angular speed, angular velocity, omega, average angular velocity is just the delta theta divided by the delta t. In other words, how far have you gone in the angular distance divided by the time it takes to do it. So the exact angular velocity is the limit as delta t approaches 0 of delta theta over delta t. So it's d theta over dt. Now, a rigid object rotates in a counterclockwise sense, counterclockwise around a fixed axis. Each of the following pairs of quantities represents an initial angular position and a final angular position of the rigid object. Which of the sets can only occur if the rigid object rotates through more than 180? Well, if the first one is at 3 radians and it goes to 6 radians, let's see, 3 radians would be up here, 6 radians would be over here. How many radians is that? Well, that's only 3 radians. How many radians are in 180 degrees? Well, there's 3.14159. So 6 radians minus 3 radians is not going 180 degrees. So here, if we start at the initial position is minus 1 radians and we go to plus 1 radians, well, that's only gone 1 radian minus a minus 1 radian, V final, or theta final minus theta initial, that's only 2 radians. Well, that's not 3.14159. Now, if we have a final position, angular position of 5 radians minus 1 radian, well, that's 4 radians. That's greater than 3.14159. So that is the answer. That is the only set that can occur since it's greater than 3.14159. It's greater than pi. Okay, a rigid object rotates in a counterclockwise sense around a fixed axis. Each of the following pairs of quantities represents an initial angular position and a final angular position of the rigid object. Suppose the change in angular position for each of these pairs of values occurs in 1 second. Which choice represents the lowest average angular speed? Well, the lowest would be the shortest. So we do theta final minus theta initial. 6 radians minus 3 radians is minus 3 radians. 1 radian minus 1 radian is 2 radians, and 5 radians minus 1 radian is 4. So it would be the shortest distance for the same time would represent the lowest average angular speed. And sure enough, it's the minus 1 radian and 1 radian, because that's a 2 radians per the time for the 1 second. The first one is 3 radians per second. The C is 4 radians per second. So 2 radians per second is the shortest of all of those. Okay, average and instantaneous angular acceleration. Well, just as the to get average speed, you take delta theta over delta t to get omega, to get average angular velocity alpha, you take delta omega over delta t. So it's W final minus W initial, or omega final minus omega initial, divided by TF minus TI. That's delta omega over delta time. So the exact acceleration, the instantaneous acceleration, is the limit as delta t approaches 0 of delta omega over delta t, or d omega dt. So you can see the correlation. Theta is angular position, x is linear position, omega is angular velocity, v is linear velocity, and alpha is angular acceleration, and a is linear acceleration. Okay, now angular velocity is a vector, and the direction of the vector uses the right-hand rule, so that if you point your fingers in the direction of rotation, your thumb is the direction of omega. So you can see in the top view, using the right-hand rule, you always have to use your right hand. If the rotation is, but looking from above, it's counterclockwise. So the vector, the omega vector, is coming, it would be going to the top. Now, if we turn it around and looking from the top direction, it's clockwise. The fingers rotate around this way. The direction of the omega vector, the angular velocity vector, is downward. Okay, and I think that's that. This is the start of the next section, section 10.2. So we'll stop it right here.